Today I'm going to be going over open muscle updates.
Okay, from the last time we were working on open muscle, the open muscle pressure sensor band. Now it's also helping Ultimate Robotics with their NRF52832 based system. So this system is a system of EMG sensors in a band around the forearm to detect when the muscles are being contracted. This is then sent to a label device that I helped them to design that was based off of the LASK4 system that I designed for open muscle. So this is the U-label device. It is a 5-finger somatosensory device. It has a reversible design, so the battery goes on the opposite side of the thumb. There's 2 Hall effect sensor spots, so that way if you reverse it or mirror it, you're going to have the battery on the other side and be able to do the other hand. Again, this is based off of the NRF52832 board, and it uses the custom 2.4 gigahertz. You can communicate about at a maximum of 2 megabits per second using this custom protocol, but our information is going to be well below that threshold or well below that limit. So the NRF52832 is a really nice little powerhouse that allows us to have a very small, relatively small package. Now, I successfully used the open muscle band OM12. That was successful. I was able with the LASK4 system, which is a 4-fingered device that I have unplugged at the moment. This is mostly a do-it-yourself kit. It was designed as such. Open Muscle is open source, open hardware, trying to get this technology into the hands of very intelligent people because this problem is solvable. And I do believe we can solve it together. So it has a interface where it measures the pistons. There's Hall effect sensors underneath these pistons, which are just a cap that have a magnet at the base. The LASK4 system successfully was able to predict finger movements based off of the pressure sensor of OM12 on the forearm. It's to a high degree of accuracy. So the success of Open Muscle 12 led me to work with Ultimate Robotics to create the same system for them. Because this is open source and open hardware, I believe that sharing this information is vital to the mission of what we're trying to do, which is to use technology to solve some issues that might come from certain disabilities, like having a missing limb, missing hand in this case, with an intact forearm. The impetus of designing this was creating an open source prosthetic sensor. Because machine learning is very good at solving this problem, associating the 12 sensors around the forearm that are measuring pressure to the 4 pistons, 4 finger movements that we're measuring. Now, it's a very specific use case. Also, if you're training this on someone with a hand, then you're going to get a different output. So this is just a process in the steps of solving this problem. We've created a successful pressure sensor system to predict finger movements. We've a relationship with Ultimate Robotics and helped them to design their own label system with their system, so people can be working on this problem around the world. Now I'm going to be focusing on the open muscle system again. I at first tried to adopt the NRF52840, where instead of pressure sensors, I was building my own custom pressure sensors by 3D printing something, and that worked relatively well. In that system, there's magnets attached. As you can see, things are sticking to this. It is a spring system that uses clevis pins and springs, and it uses just a 3D printed shell with these magnets on the edges of the pistons that are bolted on top of 2 Hall effect sensors to measure the magnetic field. So this works quite well. As you can see, they wobble all around. The reason for that is it's not desired for them to wobble around, but rather it's desirable to limit the friction in the system, to actually measure the change of the tension. This is pretty much measuring the tension of the skin on the surface. But because the muscles change properties when they contract, it's really high signal to noise ratio for measuring when a muscle is contracted. There is noise in the system, but we'll get over that. The type of machine learning we're using is going to actually look for the noise and try to filter that out just naturally through the system. So this is instead of using a clevis pin, we are actually using keyboard switches. So they make now keyboard switches that the whole keyboard switch with a magnet on the bottom instead of a switching mechanism. So instead of actually just being on or off, you're just moving a magnet closer. A lot of times people install Hall sensors on the keyboards that actually just have a threshold. And once that threshold is met, then it flips, on or off. That's a binary output. We're using linear Hall sensors. So we made our own custom PCB, and we just put some holes for the device there to rest on there. I'm gonna turn on my other light. So yes, this is our circuit board, custom circuit board. You can see there's spots underneath here for a Hall sensor, but I'm not proficient when it comes in programming in C. It is just not my specialty. I am actually going to go away from the NRF series of boards because of my lack of familiarity. And we're gonna replace the board and create this same system. Now this will be the new open muscle system. The last one was called OM12, and that's based off of the 12 sensors it had. This one will be called Open Muscle Dev Kit. The last one was a working prototype, OM12. It's not really meant for people to actually build it themselves. It is very convoluted. It was mostly just for research and development for myself to figure out a couple of things with the design. So the next version is the Open Muscle Dev Kit. This product is not meant to go to consumers by any means. It's meant to go to developers to actually work with this technology and see if they want to use it in their system. And being open source and open hardware, it has to have community support. So we want to build it in such a way that you can build the pieces with limited knowledge and work with the technology, right? It should be open and accessible. So we're going with the ESP32C3 Super Mini. Now the Super Mini is actually quite a bit smaller than the ESP ones. And this is a dev board. So it also includes a couple of buttons, GPIO access, and surface mounted, the double ones. I don't know the names of those yet, please forgive me. This is the NRF board. And then right next to it, we have the smaller board that we're gonna be using. So it's a little bit smaller, and we can free up some space on this board, make this a little less wide. There's supposed to be at least 6 of these. So I just want to go through some of the things that I'm thinking about for this project because it's nice to document them. So yeah, so we got to measure the LDOs to see if we can, I don't even know this. I'm showing my ignorance here. I don't know if I put 2 LDOs in parallel, if it will actually be able to output 3 volts at 500 milliamps. Now, in principle, I think this is probably the case. I might have to have some conversations with ChatGPT and maybe a couple of my friends I might pester. I need a working voltage regulator dropping 4.2 volts down to 3.7 volts, or maybe a little bit less, to 3.3 consistently. And this is another problem. We almost want to have a battery on each of these. Now, I've been using these really small batteries, which are nice. Like we can probably fit it on the board, but this is still a little quite big. When you're getting down on this size, small batteries are difficult. We probably want some kind of battery on each one of these. If not, we want to be able to hook in 1 battery or 2 batteries to multiple ones. So the power management is going to be a big issue for me. Probably the most difficult one that I have to solve. Yeah, so if you know a little bit about this and you want to help, that would be wonderful. Trying to keep it low cost, trying to limit the magnetic field. I got my work cut out for me. Okay, so now we'll get to work. So this is what we have at our disposal. We have a breadboard, we have the ESP32C3 Super Mini, some header pins, and we have some other ones. We might need to test a couple of them in parallel with 1 battery supply. We have some LDOs that are capable of 250 milliamps. This is surface mounted, and then these are just normal pins. It's okay, that's pretty close. Good, there's that super small thing right here. That one little diode, it looks like. A resistor. Okay. Those two, but these look good. Should be good for us. So yes, what we need to do now is to flash MicroPython onto the microcontroller. Let's see if we can do that relatively easily. Okay, so we needed to get ESP tool. I guess I don't have ESP tool, so we're gonna clone it. So let's open up Explorer, ESP tool master. We are going to copy this command, and it is going to be COM8. No module named, init hex, Intel hex. So Python tech m pip install Intel hex. Usually it's supposed to do that for you. Okay, now it looks like it's successfully erasing the flash, so I might be turning this into a brick, which would be kind of fun. Hard resetting via reset pin. Chip erase completed successfully in 15.7 seconds. Hard reset via RST pin. Okay, I will do that. I did that. Let's see if Thani still has it in COM port 8, which it is, interestingly enough. So then we can copy this, put it here. Okay, so we are going to backspace and type in ESP. Yep, there, this one. And then COM8. Baud rate is 46800, right flash Z, and we can hit enter. And this is MicroPython version 1.22.2. Cool. Hard reset pin. Gonna unplug it, plug it back in. Let's print hello world. No, it actually worked, and it has a boot. That's awesome. Okay. Network connected, yes, and it got an IP address. This is awesome. So this is good enough. So what we have is So we have the code working. It's connecting to Wi-Fi, so it's pretty much going to be pulling the amount of amperage that we want to measure right now. So this should be pretty good. A good rough analog. It's not too much of a problem. And so we're going to see the consumption. What? Nope. That did not look good. That's really bad. Let's just leave. We're just gonna turn this off. Okay. Maybe I just fried the board. So we'll see what it is now. There we go. Okay, so the LED is blinking. We're at, it's taking 100 milliamps. It's averaging here, 25. Okay, it might jump up to 100 again. I think that's when it's actually using the Wi-Fi, and it might have aired out, which is good. So I don't know what I was doing with the other setup. We're just gonna leave it there. So it looks like we hit a cap, which we can actually go back and look at the recording to see what was done. So let's, we're gonna hard reset it again by unplugging it. And this is ground, plug it back in. Okay, 20. The LED flashing does do nothing, pops up to 90. More than 100, 98. I think that's it trying to connect to Wi-Fi. And then once it's using Wi-Fi, it should be sending. So I wouldn't doubt if it stayed up there. So it looks like we're averaging while it's running a peak of 100 milliamps and it's staying within the bounds of the LDOs that I purchased. So this might be good, but we want to make sure that it doesn't go away. So now we're gonna just create a stable connection with the Wi-Fi and then come back, and then we will look at it a little bit better. So, and we want to make sure that it actually connects. So I'm going to hit stop, and it usually stops and resets it. Sometimes I have to do this twice. This is also why I have the throw 5. The throw 5 code just has the LED blink 5 times, because sometimes these microcontrollers with MicroPython, you have to catch them at a certain time of being plugged in order to connect. So having a delayed boot is helpful for just being able to connect to it. There we go. See, it's trying to connect. That's pretty good. So it's running this program. And okay, so we're gonna go ahead and check the power consumption now. So now it should connect and stay connected, and we're gonna see a higher power consumption because it's gonna be sending packets. So it's 21 milliamps. Okay, popping up to 100, and there we go. We're seeing the higher power consumption because it should be doing its thing. Should bump up to 100 another time. There we go. And now it looks like it's sending packets. It's okay. So now it looks like it's connected because of the power consumption and what we saw when it was connected to the computer. It is actually actively sending packets. I can check a UDP server that I'm setting up, but right now we're just measuring the power consumption. So it looks like we're peaking at about 100 milliamps, which is great because the LDOs that I have, they are only rated to 250 milliamps. So we can actually do some measurements with these and hopefully power this device. So I'm gonna mimic a battery now, and we're gonna see if this LDO operates properly. I am gonna have to check the pins. So we are going to move over the power on the left side, power rail. And let me check what these pins are. I don't even know. Okay, I have the MCP 1700. Let's look at the data sheet. And the data sheet says we have the left is ground, V in is the middle, and V out is the right. Okay, so we got ground on the left, V in, and then V out. So I'm supplying it with 4.03. Okay, 4.03, it's kind of the battery. It's consuming quite a bit. It should be running. And this thing is gonna dissipate the inefficiency as heat. Since I'm so close to 3 volts, it should be fine. But I do wanna measure the voltage here. So I'm gonna switch this back to voltage. Make sure it's selected. We are going to measure how many volts are out, and we're getting 3.28. So this should be able to go upwards of 6 volts. And we should, 5, and it's still going to maintain there. It can go up to 6 volts, I don't want to push it. We can see that this is actually kind of stopped. So I'm going to reset this. and we should see these flash 5 times. And we're not actually consuming that much power. I'm surprised, which is probably, you know, pretty accurate because the voltage is pretty low. And the voltage out is at 3.28, 3.29. So let's disconnect this again. I'm going to disconnect the power and connect it back. And this is going through the LDO, which, to be honest, I could probably just power this directly through the 5 volts in, but... So yeah, so we know its consumption rate. It can get as high as 120. We'll just, you know, double it, say it can get as high as 200, because it probably can in certain circumstances. We're also not powering the Hall effect sensors, so we might want to measure that too, but this is within the tolerances that I thought it was. And yeah, our LDO is not getting hot. So just so you can see, this is the setup there.
So wonderful, we found the consumption rate. We also learned that the LDO that we purchased would be usable on the new Open Muscle dev kit. So next time we'll probably be working on the PCBs, but I appreciate you watching this. Please leave a thumbs up on this video if you liked it. That helps me out quite a bit. And leave your question or comments in the comment section below. As always, let's see if we can make a positive difference in this world. Till next time.